So the second order partial derivative with respect to r, sometimes written as z double r, which means the second order partial derivative with respect to r, okay, is nothing else but the partial derivative of r of partial z partial r. Okay? Which means first I have to find how much is partial z partial r. So let's do that first of all. Partial z partial r is equal to, so one more time, z depends on x and y, x depends on r and s, and y depends on r and s. So to get from z to r, I need to do partial z partial x partial r plus partial z partial y partial r. Okay, so as you can see, I always interchange between these notations so we can get used to both of them. So by the chain rule, this is partial z partial x times partial x partial r plus partial z partial y times partial y partial r. Okay, so far nothing new. So let's figure out how much is this. Z is not determined explicitly in terms of x and y. That means partial z partial x is going to stay as it is, or just change the notation if you want, just to save some time. So partial z partial y, we cannot express explicitly because we don't know what is the function z explicitly in terms of x and y. Now partial x partial r is right here. I treat everything that's not r as a constant. S squared is a constant. Derivative of s squared is 0. Derivative of r squared is 2r. Derivative of, so 2s is a constant. Derivative of r is 1. So times 2s. Okay? Or this can be written as 2r partial z partial x plus 2s partial z partial y. Okay? Now I'm ready to just start, okay? Be careful, this is going to be a long process, evaluating the second order partial derivative with respect to r. So, second order derivative of z with respect to r is the partial order derivative of r with respect, the partial order derivative with respect to r of partial z partial r, but this expression is right here. So that becomes the derivative of 2r partial z partial x plus 2s partial z partial y. Okay? And now what do I have? I have a derivative of a sum, and we know that derivative of a sum is nothing else but the sum of the derivatives, right? So this is equal to derivative of this expression plus the derivative of this expression. I'm doing this very slowly, step by step. 2s partial z partial y. Okay. Now I'm differentiating with respect to r, right? So what are going to be the constants? This expression, this is a constant, and this expression, this whole thing is the constant, right? Pull the constant out. Taking the constant outside, because the derivative of a constant times a function is the constant times the derivative of the function. And here, this is the constant 2s. Okay. Now we go one step further. What is going on here? Okay. I have r times partial z partial x. So if I find the derivative of two functions depending on r, I have to apply the chain rule. So that is going to be equal to 2. Derivative of r with respect to r is just 1. So in this case, that's going to be d dr of r, which is 1. 1 times partial z partial x plus r times the partial order derivative with respect to r of partial z partial x plus 2s partial derivative with respect to r of partial z partial y. And now let's just drop this parenthesis right here. The square brackets, 2 partial z partial x plus 2r plus 2s, the partial derivative with respect to y, or r of partial z partial y. And as you can see here, I'm not doing anything yet, okay? Because here I have to be very careful. So here I need to stop for a second. So far we didn't do anything but use the second order partial derivative was the derivative of the first derivative. Derivative of a sum is the sum of the derivatives, okay? Then we pull the constants out. Then we apply the chain rule, the product rule, and then I just drop the square brackets. So I didn't do anything new. But here I have to stop. In order to evaluate these two derivatives, I need to slow down a second, okay? Why? Because similarly to z being function defined in two variables, right, where I had to build this diagram or tree, whatever you want to call it, its derivative will also depend in x and y, which means that partial z partial x, which can be written as partial z partial x, right, also depends in x and y, and from there x depends on r and s, and y depends on r and s. And similarly, partial z partial y depends on x and y, and these two functions are defined in two variables, r and s. So finding partial r of partial z partial x, I have to find this derivative right here, which is going to be partial x of partial z partial x times partial x partial r plus partial y partial z partial x times partial y partial r. So when you're looking for the second order partial derivative and applying the chain rule, you have to be careful about that second derivative, because the first derivative is also a function of two variables. So don't just go into conclusion that this is going to be second order derivative of z with respect to x or r or whatever you might be, okay? So let's follow this diagram and evaluate how much is going to be, and evaluate how much is going to. Please stop me at any moment. I know that this might be challenging, so if you have a question, please ask me, okay? So let's see first how much is the derivative, partial derivative with respect to r of partial z partial x. I'm doing this problem, right? This derivative, only this expression. Okay, so that's equal by these three, right? The partial derivative with respect to x of partial z partial x times partial x partial r, okay, plus this one here. Partial derivative with respect to y of partial z partial x times partial y partial r. Now this is the second order derivative of z with respect to x. Because if z is not defined explicitly in terms of x and y, its derivative is not defined explicitly in x and y, so this is all we can write for the second order partial derivative. Times partial x partial r was already evaluated. Now I even forgot how much was that. X was r squared plus s squared, right? So partial x partial r is 2r plus, now I'm looking for the derivative of z, sorry, derivative with respect to partial derivative with respect to y of partial z partial x. So that's the second order mixed derivative, first with respect to x, then with respect to y, times partial y partial r is 2s, okay? This expression right here, it's only this part. Okay, is this expression right here. Now, let's do this one. Okay. Partial order derivative with respect to r of partial z partial y, this one right here, is going to be what? Well, how are we going to go, how are we going to get from partial z partial y to r? First, the partial order derivative with respect to x. So that's partial x partial z partial y times partial x partial r plus partial y of partial z partial y times partial y partial r. Now that's equal to, this is going to be the mixed derivative, second order partial mixed derivative times partial x partial r was 2r plus the second order partial derivative with respect to y times partial y partial r was 2s. Okay. So now I can go back and continue from stop, right? Continue from where I stopped right here. Because now I have the expressions, these two expressions, I know how much they are. So that's going to be, right, 2 times partial z partial x plus 2r times, all right? Now I'm gonna mix in the other notation just as a practice. Z double x, the second order partial derivative of z with respect to x twice, times 2r plus the second mixed derivative, xy times 2s. Okay, plus, so again, this expression is just this one right here. plus 2s. Now, the partial derivative of with respect to r of partial z partial y was evaluated here, so I just plug that in here, changing the notation just because. So the mixed derivative first with respect to y, then with respect to x times 2r plus z double y, right? The second order partial derivative of z with respect to y twice times 2s. And now drop the parentheses, keeping in mind the Clairaut's theorem, which says what? That the mixed order derivative is the same. Okay, so let's see what do we have. 2 times partial x partial z plus 2r times 2r is 4r squared. The second order partial derivative with respect to x twice plus 2 times 2 is 4rs. The second order mixed derivative. Now I move on, dropping the second parenthesis. 2s times 2r is 4rs. The mixed derivatives are the same by the Clairaut's theorem, so I can write, instead of derivative of z first with respect to y, then with respect to s, by the Clairaut's theorem, that's the same as the second order derivative first with respect to x, then with respect to y, plus 2s times 2s is 4s squared, the second order partial derivative with respect to y twice. And finally, we can just add the terms, the like terms, right? And those are just these two terms. That's 4r squared z double x plus 8rs, the second order mixed derivative, plus 4s squared z double y, or the second order partial derivative with respect to y. So these questions really require a lot of writing. Okay, they're not easy questions. This is where we started, finding the first order partial derivative, and then we attacked the second order partial derivative. When I got into applying the chain rule to the first order partial derivatives, I had to stop for a second, evaluate those on the side, and then plug everything back in and simplify the expression. Any questions? Any questions?
All good.
All good, okay. Let me just, I have some technical problems here. Give me a second, please. Should we do another example like this, or you guys are okay?
I think I'm fine.
Who is that? Me.
I'm Charles. Hi.
Are you okay?
Yeah. All good.
Let's do another one.
Okay, sure.
Let's just do this one, the same problem. The second order mixed derivative, partial r, partial s, right? This one says what? Find first the derivative of z with respect to s, and then with respect to r, right? What do we know? We know how much is partial z partial r. So first with respect to r. So we're going to use the Clairaut's theorem that this is equal to partial s partial r, right? Which means I have to find the partial derivative of, with respect to s, of partial z partial r, right? But I have the expression for this derivative when I did the previous problem. So partial z partial r was 2r partial z partial x, 2r partial z partial x, plus 2s partial z partial y. Okay, so we're going to speed up just a little bit here. Now this is going to be a constant, right? So that's 2r, the partial derivative with respect to s of partial z partial x, plus 2 times the derivative of s with respect to s is 1. So by the product rule, that's derivative of s, it's 1 times partial z partial y, plus 2s times the partial derivative with respect to s of partial z partial y. Now I'm going to bring this diagram back. And first I want partial z partial x, but now I want the derivative with respect to s. So that's going to be this derivative here with respect to x, partial x of partial z partial x, times partial x partial s, plus partial derivative with respect to y partial z partial x, times partial y partial s. Okay? So that's 2r times derivative with respect to x of partial z partial x times partial x partial s, plus derivative with respect to y of partial z partial x, that's it, times partial y partial s, plus this stays as it is. Okay, it's the same, just different notation, plus 2s times, now this derivative with respect to s. So I need to get from here to here, that's partial x partial z partial y times partial x partial s, plus the partial derivative with respect to y partial z partial y times partial y partial s. So you can see that this problem becomes much quicker, right? Once we have some kind of intuition or practice about it. So this is equal to 2r. This is the second order derivative with respect to x, so z double x, partial s partial x. I already forgot what x is. Can somebody remind me? I think it's 2s, right? So here, let's say, how much was x and y defined? R squared plus s squared and 2rs. Okay, so partial s partial s is 2s, plus this is the mixed derivative, second order mixed derivative xy by the Clairaut's theorem. Well, that doesn't change, first with respect to x, then with respect to y. Partial y partial s is 2r, plus this is the partial derivative with respect to s, to y, plus 2s. This is the mixed order partial derivative, first with respect to y, then with respect to x. Partial x partial s is 2s, plus z double y, right? Times partial y partial s is 2r. Okay? Which is equal to 4rs z double x plus 4r squared, the mixed derivative, plus 2zy plus 4s squared is the mixed derivative. So because we're going to add them, I'm just going to rewrite this as first with respect to x, then with respect to y, plus 4rs z double y. And then which one we can add? Similarly to the previous, we cannot add any of these. Okay, so this is just going to be 2zy plus 4rs z double x plus 4rs z double y plus 4z, the second order partial derivative, which was the mixed derivative, r squared plus s squared. So you can see you don't really, once you have the sense of the second order partial derivatives alongside with the chain rule, then it becomes, you can do this in one go, right? Any questions? And then the last section in this chapter is the implicit differentiation. Okay, so let's say we are talking about a function defined in x and y that is equal to 0, right? And it's defined implicitly as a differentiable function of x. In other words, say y is equal to h of x. Okay? So now define, let's say w is equal to okay, so y is some function in terms of x. Okay? Let's find the derivative on both sides with respect to x. So and this, as we said, is equal to 0. So 0, the derivative of 0 is 0, is equal to partial w partial x, right? Where partial w is capital F. But for this one, we have to use the chain rule. So I have partial f partial x times, so this function f depends on x and y, right? And this one stops here, and this one is defined in terms of x. Okay? So by the chain rule times, now I have dx, right? Plus partial f partial y times y is just defined in terms of x, so I have dy dx. This is just 1, okay? So that's partial f partial x plus partial f partial y times dy dx. And all of this, as you can see, is equal to 0. Okay? In that case, how much is dy dx? Well, let's just express dy dx from here. Negative partial f partial x. So only dy dx is equal to negative partial f partial x over partial f partial y. Implicit differentiation into variables. Any questions? Okay, so let's do an example. Find dy dx where x squared sorry, y squared minus x squared is equal to sine of xy. Okay. Well, first I have to define this function in two variables w. And I'm going to do that by bringing everything on one side of the equation. Okay, and that's equal to 0. Okay, and then I just apply this formula right here. dy dx is negative partial f partial x over partial f partial y. So partial f partial x is negative. Derivative of y squared with respect to x is 0. Derivative of x squared with respect to x is negative 2x. Minus derivative of sine is cosine of xy times, by the chain rule, derivative of x with respect to x is 1 times the constant y times y. Over, and now the partial derivative of f with respect to y, it's 2y minus cosine of xy times x. So now make this expression slightly better by dropping the parentheses, and you get 2x plus y cosine of xy over 2y minus x cosine of xy. Any questions? For a function defined in three variables, the implicit differentiation would be partial z partial x is equal to negative partial f partial x over partial f partial z, and partial z partial y is going to be equal to negative partial f partial y over partial f partial z. Any questions, guys? Questions?